You know that old saying, seeing is believing? Well, in astrophysics, that's a huge problem. I mean, the most massive things in our universe, dark matter, black holes, they're just completely invisible.
You can't put a galaxy cluster on a bathroom scale, that's for sure.
Exactly. But we've got this stack of research here on relativistic astrophysics, and it says we don't need to see them to weigh them. We just have to watch how they mess with the light behind them.
It's a bit like trying to see the wind. You can't see the air itself, but you can see the trees bending.
Okay, I like that.
In our case, the wind is gravity, and the trees are light beams traveling across billions of years. We're doing a deep dive into gravitational lensing.
Which is basically using the universe's own geometry as a giant telescope. Now, looking at the history here, this wasn't some idea that just appeared with Einstein.
Not at all.
The sources actually point out a guy named Johann von Soldner, back in 1801, calculating this with Newtonian physics.
He was. Yeah, the Soldner treated light like a stream of tiny particles. He figured, if gravity pulls on rocks, why shouldn't it pull on light?
And he wasn't wrong, technically. Gravity does pull on it. But this is where the factor of two mystery comes in, which I think is the coolest part of this whole story.
It's the whole story, really.
So Einstein publishes General Relativity in 1915, and his prediction for that bending angle isn't just different from Newton's.
It's exactly double.
Exactly, a perfect factor of two.
And that discrepancy is the key. Newton was only accounting for 1/2 of the picture. He saw how gravity affects time, what we call time dilation.
So he got the time component.
Right. But he missed the other part. General relativity says gravity doesn't just slow down time. It physically curves space.
So you have warped time plus curved space. You add those two effects together, and you get double the deflection.
And that was the make-or-break test. When Eddington and Dyson went on that 1919 solar eclipse expedition, they weren't just looking to see if starlight bent.
They were checking how much it bent.
Exactly. Was it the Newtonian amount or the Einsteinian amount? And the universe, well, it sided with Einstein.
Okay, so let's get into the toolkit this gives us. The papers talk a lot about the thin lens approximation.
It simplify the math, basically. Instead of calculating all the complex curvature across the universe, you just pretend it all happens at once.
Like it's passing through a single sheet of glass.
A single lens plane, yeah. It lets you compare two simple things. Beta, which is where the source galaxy actually is.
And theta, which is where it looks like it is in our sky. The difference between those two tells you the mass of the object doing the lensing.
And it all relies on something called Fermat's principle.
Which says light takes the path of stationary time, not necessarily the straightest path. It wants to be efficient.
Right. Near a massive object, the shortest path in terms of distance might actually take longer because time itself is slowed down by gravity.
Wait, so the path is longer, but it's also slower.
That's the mind-bending part. The sources break it down into two delays. First, there's the geometric delay. The curved path is just physically longer than a straight line would be.
Makes sense. A curved road is longer than a straight one.
But then there's the Shapiro delay. This is the gravity slowing down time part. The light is essentially wading through this gravitational well, and that slows its progress.
And all that delay and bending creates the distortions we see. You get convergence, which magnifies things, and shear, which stretches them.
That's where you get those iconic banana-shaped arcs in telescope images.
Or if everything lines up perfectly.
An Einstein ring. A perfect circle of light.
But this isn't just about making cool desktop wallpapers. This is how we actually map the invisible universe.
This is the tool. Strong lensing, where you see multiple images of the same distant object, lets us map the distribution of dark matter with incredible precision.
And it gives us an independent way to measure the expansion of the universe. I mean, this is crucial for the whole Hubble constant debate.
It is. It comes down to those time delays we talked about.
Because if a lensed quasar flickers, we won't see the flicker in all the images at the same time, right?
Exactly right. Light from one image might have taken a path that's, say, 3 weeks longer than the light for another image. So you see one flicker today.
And the other one 3 weeks from now.
And if you know that time delay and you know the speed of light, you can calculate the actual physical distances involved. It's a purely geometric measurement.
So you can calculate the Hubble constant without needing any other cosmic yardsticks like supernovas.
It's an incredibly elegant solution, but there's a catch. The sources end on this slightly unnerving idea called mass sheet degeneracy.
I was hoping you'd bring that up. It sounds like a loophole in the math.
It is, kind of. The math shows that you could add a uniform, invisible sheet of mass across the entire lens plane.
Okay.
And it would change the actual time delay, but it wouldn't change the shape or position of the images we see at all. Everything would look identical.
So our calculation for the distance and for the expansion rate of the universe could be wrong by a certain factor, and we have no way of knowing.
We could be looking at a mathematically perfect model that's just physically wrong. It's the ultimate unknown unknown.
A humbling thought. We've mastered the geometry, but the universe might still be hiding the true scale from us. That's it for this deep dive. Thanks for listening.